So in chapter 9, we're going to be talking about three-dimensional geometry, and while that sounds kind of scary, it's actually, I think this is one of the easier chapters of the entire course. So today we're going to do the first two sections. This first section is mostly vocab and a review of some formulas. So the way we're going to do the vocab is we're just going to kind of look at pictures and talk about the names for them, because we're not proving anything. We don't need like a really tight verbal definition of something. We just have to kind of like know it when we see it, or if I hear the name, know what it looks like is good enough for us. So that's all we're going to kind of do here. Everybody cool? All right. So if I look at the first picture here on the left, what is that shape? Cube. Yep. The next picture, what is that? Rectangular prism. Good. Now, or you might call it rectangular solid. Those two terms here could be used interchangeably. Or what I think is kind of a popular European term, you might call this a cuboid. I don't like that term, but I see it pop up here and there, especially in the IB materials. This is an IB SL topic. So when we call something a prism, that's a more generic name. So when we talk about a prism, that's going to be a three-dimensional figure that has two bases that are parallel and congruent, right? The ends of this box are the same size and shape. And if I take this box and I cut it, make a cut parallel to the bases, and I look at the cross section of what I just cut, it should also be congruent to the base. So it can't like bow tie in the middle or something. You know what I mean? To be a prism anyways. Everybody's okay with that? Okay. This next guy, what are we going to call that thing? Yeah, so it's a pyramid, and we'd want to be specific because pyramids can have lots of different shapes for their base. So we'd want to be specific there and indicate the shape of the base. In this case, that appears to be a square. And what's this last shape here? Looks like a doorstop to me, or a ramp. Yeah, that's a triangular prism. Good. So again, we can see the parallel bases are triangles there. If you take then a cross section that's parallel to the bases, you're going to get that same triangle shape as your cross section. You know what I mean when I say cross section? Like imagine cutting a loaf of bread. Like every slice you take looks like the end of the loaf of bread. Same shape and size-ish. Okay. Moving on. So again, shape on the far left, what do we call this thing? Cylinder. Yeah. Now, kind of technically, could you think of a cylinder as a prism? Yeah, right? The bases are circular. You take a cross section, it's still going to make a circular shape. Could think of this still as a prism. I don't think that anybody really calls them that, but could still be classified as a prism. How about the second object here? It's kind of a trick question. Yeah, it's another rectangular prism or cuboid or whatever you want to call it. And then the third shape there. So again, it's a rectangular prism, but we'd want to be a little bit more specific between the two, right? The one on the left and the one on the right, although they're both rectangular prisms, one is kind of leaning and the other is like standing straight up. So the one that's standing straight up, basically the faces are making a right angle with the base of the prism. Everybody can kind of see that it's straight up and down. They're perpendicular. We're going to call that a right rectangular prism. And the one that's kind of leaning, like somebody sat on it and kind of squished it, we'd call an oblique rectangular prism. And those terms really can apply to any three-dimensional object, right? If the faces are perpendicular to the base, we'd say that that's right. And if it's, well, let's just say if it's like straight up and down, it's right. And if it's like slanted or leaning or whatever, it's oblique. Cool? How about this fourth thing? Well, the fifth thing is a pentagonal prism, sure. You're just one ahead of me. That's okay, no worries. What about that one in the middle there that we skipped? Yeah, so being as specific as we can, it's a right triangular prism. Everybody's cool? Again, just kind of having a conversation, talking about some names, how we name stuff, what are things called, what are some of the adjectives we use, you know. Am I going to make you do like a matching thing on a test and like match the shape with the name? No, man, I'm not interested in that. What do we need to be able to do? Like if I say the name of the shape in a story problem, you should know what it looks like so that you could like sketch a picture. That's what I need you to be able to do. So like, you know, it's not that big of a deal. This guy right here, as specific as we can, what would we call this? Yeah, so we call this a right square pyramid. As an additional piece of vocab, the tip of the pyramid, that point has a name. It's called the apex. I don't remember in geometry if we use that term or not, but it's a pretty common one. And again, here the rightness is because the height is perpendicular to the base there. Everybody's cool with seeing that? Straight up and down is good enough, though, for us. You know what I mean? It's one of those, like, you know when you see it, if it's right. It's probably the way you would draw it, even if I didn't put the right in there, right? Nobody's going to draw like a pyramid about to fall over. It's also hard to draw. The next four shapes, what's the first one there on our left? That's a sphere. Okay. The middle one, or I'm sorry, the second one? Hemisphere, way to go, global politics. And the third one, it's still another cylinder. We just threw it in again. The last one is, that's a cone. And again, on a cone, the tip of the cone is the apex there again. Everybody happy? No big deal. So far, so good. Just reviewed a bunch of names. A lot of these things are things that you hopefully remember from your previous math courses, specifically geometry. Some of them might be a little bit of new vocab, and that's okay. It's just a little bit of vocab. Just talking about shapes, man, you know. At this point now, let's review some area and volume formulas that you potentially would have seen in your geometry course. So area of a triangle, what's one formula for that? Yeah, 1/2 base times height. But for chapter 7, we know that there's a couple of other area formulas we could use. Does anybody remember one of the other ones? Yeah, 1/2 AB sine C. And the other one? Yeah, Heron's formula, the one with the S's in it. Yeah, we'll do that. So the square root of s times s minus a times s minus b times s minus c, where s is that semi-perimeter. Bless you. Sure thing. How about the area of a parallelogram? Who remembers that from your geometry course? Yeah, just base times height. But the thing you have to worry about there with your parallelogram is that the height isn't necessarily a side length. Now, in the case of a rectangle or a square or something, sure, the height is a side length, but in general, the height is not necessarily a side length. Everybody's cool with that? How about the area of a trapezoid? Ooh, this one's a little bit tricky. Who remembers that one? Yeah. So I think when I learned it, we called it B1 plus B2. But it's the average of the two bases. Remember, in a trapezoid, we have exactly two parallel sides. We call those the bases, and you abbreviate them as B1 and B2, and then the height of the trapezoid could be one of the other side lengths, but doesn't have to be. So the area of the trapezoid is just the average of the length of the bases times the height. Again, what letters you want to use to do that, to describe those parts is, these are the ones that I used. You know what I mean? Circumference of a circle. What was that one? It's not pi r squared. 2 pi r, yep. Or pi d, where d is the diameter, which is the same thing as 2 radius, but whatever. Area of a circle, that was the pi r squared. Popularly confused formulas, because you hear circle and you're like, pi r squared, and you miss what the measurement was there. How about the area of the curved surface for a cone? So if you have a cone, right, the circle part, the base of the cone, is actually flat, even though that's a round shape, but it's a flat surface. The ice cream cone part that you'd hold on to is actually the curved surface. Does anybody remember how to find the area of that curved surface? It's actually pi r L, where L is what we call the slant height. So if I have this cone here, ABC, the segment BC would be a slant height. Why do you suppose I'm using the script letter L here and not just like the regular print letter L? Yeah, the regular print letter L looks like 1, and boy, that's a Mr. Kulik move to get confused as to like what you just wrote down, what symbol you just wrote down, and your L turned into a 1. To prevent try to outsmart myself, I'm going to use the cursive L whenever I'm using the letter L. You know what I mean? Still haven't found a good method for the O's and the zeros yet, but thankfully we don't really call anything O. I guess you could put a slash through the zeros. But I use so many more zeros than I do O's. I'd rather use a different letter O, like do something, like do the cursive O or something on it. I think, because the zeros I use all the time, right? That comes up a lot more often than the letter O does, in math class anyways. Volume for the cone, does anybody remember that one? Yeah, well, it's 1/3 area of the base times the height. And in the case of a cone, the base is a circular shape. So pi r squared would be the area of the base. Notice here I'm going to use the capital B as the area of a base for a three-dimensional figure and the lowercase b to represent a side length that we're calling the base in an area formula. Is that okay with you guys? Okay. So the area of the curved surface of a cylinder, again, a cylinder has a flat circle on top and bottom, but the whole side of the place where you'd hold onto your can or whatever, that's the curved surface. This one's a little bit easier. Does anybody remember this one? Yeah, so it's the circumference of the base times the height. And since the base is a circle, 2 pi RH. That's good. Do you remember the volume of a cylinder? Yeah, I'm going to say area of the base times h, but in a circle, or for a cylinder, the base is a circle, so pi r squared h. In general, any prism, the volume is area of the base times the height for any prism. But since we're talking about a cylinder specifically where the base has to be a circle, we'll be specific and say pi r squared h. How about the volume of a sphere? This was another kind of weird one. Yeah, that was it. 4/3 pi r cubed. Again, I can't remember back in the day when I did teach a geometry course. I think I derived this. It's a little bit of a weird derivation. If you take the AP Calculus course, my suspicion is whoever's teaching it, when you do like volumes of revolution, will derive the volume of a sphere formula using calculus. It's a little bit of like using a, like a shotgun to kill a fly kind of thing, but it's kind of neat seeing it work out. Surface area for a sphere. Well, it's like using a tool that's kind of more powerful than you need.
Like the math terminology?
Yeah.
No sense.
Oh, no. That's when you take AP Calculus. If you do. If you wanted to. It's probably something you do. It'd be late second semester. So, anyways. Yeah, I don't expect, should have been like, oh, I don't know what he said there. Maybe if, in a year from now, if you're in the AP Calculus class, you'd be like, I remember Mr. Kulik said something about this, and look, we're doing it right now. Like you all have that good of memories. But now that we've talked about it for a minute, kind of made some jokes about it, maybe you will. Who knows? I don't know. Surface area for a sphere, do you guys remember this one? This is a little bit of a surprising result. Yeah, 4 circles. That seems weird, but that is indeed what it is. The volume for a pyramid. Keep in mind the pyramid can have lots of different shapes for its base. We're not saying square pyramid here. We're just saying any pyramid. So just 1/3 times the area of the base times the height. Again, if the base is a square, length times width or whatever, but what if it's a pentagon or something weird, like becomes kind of a nightmare if it's not a quadrilateral, because there's a kind of a hassle to deal with. But we'll talk about, I think we have an example at some point where we see a non-quadrilateral based prism or pyramid or something. I'm trying to remember. Not today. And in general, I mentioned this earlier, the volume of a prism is just the area of the base times the height. So in a rectangular prism, the base is a rectangle. So length times width times height. Everybody okay there? From here on out, the next 3 lectures for 9.1, 9.2, and 9.3, I'm going to do via PowerPoint because it involves drawing a lot of pictures in 3 dimensions, and Mr. Kulik's an okay artist, but like to do a good job there is going to take a long time. So I just made some PowerPoints to kind of streamline that process a little bit. Those PowerPoints are available here on My Notre Dame in the download section if you wanted to go and look at any of those. That being said, for those of you that are like regular note takers, you may want to take it easy on trying to draw all the pictures here, because it gets to be, they're kind of tough to draw in 3 dimensions on your 2-dimensional paper and do like the shading and stuff that's going on. So maybe this is a better just kind of like, I'll look at the PowerPoints later or whatever kind of thing. You know, whatevs. All right. So today in section 9.2, we're going to talk about lengths within 3-dimensional solids. Basically what we're talking about is like we're going to be looking for the length of some segment inside of some 3-dimensional figure. So the main tool that we're going to be using to do this is a calculation triangle. So by a calculation triangle, all we're going to be talking about is some right triangle that's embedded inside of our 3-dimensional figure. So if I have the right square pyramid here, an example of a calculation triangle might be this triangle ABC. Okay with that? I'm particularly interested in right triangles because why? I got SOHCAHTOA I can use. I got the Pythagorean theorem I can use. I don't run into any weird 0, 1, or 2 triangle situations. It's all very straightforward. This is just my preference is, can I do this with just right triangles? Okay. Now, probably the most challenging part of this whole chapter is having enough 3-dimensional like imagination to like find those or find the relevant calculation triangles inside of your 3-dimensional figure. To help a little bit with that intuition, we're just going to buzz through a couple of 3-dimensional figures and point out some of like the unexpected or unusual right triangles that exist inside of them. So we'll do some examples here of doing that. So inside this rectangular prism or cuboid, one example of a calculation triangle would be this pink guy, EAD. That should be pretty obvious. I mean, it looks like a right angle here at A. But this blue one, triangle FGD, is also a right triangle. The right angle is here at G. And I know that has to be a right angle because I know the face FBCG is perpendicular to the face GHDC. Yep. So I know that the segment in the FG that's in the plane of the FBCG and the segment GD that's in the plane GHCD also have to be perpendicular. Oops. So those are my 2 calculation triangles that I've highlighted here. So everybody can kind of see that. So don't be concerned, even though, hey, on my sheet of paper, that doesn't look like a right triangle, right? That looks like an acute triangle, right? Still is a right triangle. You have to use a little bit of imagination to see it in 3 dimensions, but once you've kind of imagined it in 3 dimensions, you should be like, okay, yep, that's a right triangle. What you're seeing here is that because you're taking a 3-dimensional object and projecting it down into 2-dimensional space, you're getting a distortion. The same thing happens on like your maps in a history class. If you look at a map in your textbook, Greenland oftentimes looks huge, like it's the same size as South America. Greenland is not that big. The landmass of South America is much, much bigger than Greenland. What's happening is that you're getting a distortion in the things near the poles as a result of projecting the 3-dimensional object in a 2-dimensional space. So there's actually a couple of different ways to kind of do that projection that distorts things differently. The common projection that we use, I think, is called the Mercator Projection, and really distorts things in the like towards the poles. So like Europe tends to look bigger than maybe it should. Probably a we chose that projection as a result of Eurocentrism from when we started standardizing the maps that we were using. But anyways, if you ever watch the show The West Wing, there's an episode where they talk about map projections, and it's my favorite episode. It's an all right show. Continuing on, I'm going to grab the door. So again, here's another prism. We have a fairly obvious right triangle in pink there. EFC, angle F definitely looks like the right angle. Everybody should probably have no problem identifying that as a right triangle. But the blue one there is also right triangle. Angle B is the right angle. Since this is a right triangular prism, I know that this edge is going to be perpendicular to the base, so I know angle B should be a right angle. Everybody's okay with that? Okay, let's look at another one. So here's a square pyramid, or a right square pyramid anyways. Again, the angle or triangle in blue here, EFM, looks like a right triangle. It's a right triangle. But the pink one, EFA, that definitely looks like an obtuse triangle on the sheet of paper, is still a right triangle. I know since this is a right pyramid that the height is perpendicular to the base. So that segment EF is perpendicular to any segment in the base. So that's still a right triangle. I know. Who's frustrated? Don't be frustrated. Just close your eyes, imagine 3 dimensions. Yep, I see it. I see it. This is often the most challenging piece, is to just like, can you see it and see all the possibilities in 3 dimensions and pick out the one that you need? All right, so let's start doing some examples of actually doing some solving segments. In general, when I solve a story problem, my plan is going to be to sketch a picture, although typically for questions involving a 3-dimensional solid, that picture would be given to you. Identify the calculation triangles that would be relevant based on the given information. Typically, I like to sketch the calculation triangle then off to the side because the picture gets a little bit busy if I try to draw all the calculation triangles and label all the triangles inside of the same picture. I usually like to draw the triangle off to the side and then solve for the pieces that you're looking for. So my first example says a shoebox that's 32 centimeters long, 18 centimeters wide, and 11 centimeters high. And you want to calculate the length of the longest rod that'll fit inside the box. So close your eyes for a moment. Think about a shoebox, and you're trying to fit the longest stick possible in there. How is that stick going to lay? Yeah, but diagonal from the bottom to the top, right? Yeah. So like if this is our shoebox, we're talking about the stick going from, say, the corner A up to the corner G, right? So diagonally from the bottom of the box to the top of the box. Does that feel right to you guys? Okay. So there's my calculation triangle that I've kind of sketched in there. So if I look at this, it's like, okay, well, I know side GC because that's just the height of the box. I'm looking for side AG, but I also don't know side AC, right? So in order to solve this for side AG, I'm going to need to find AC first because I don't have that yet. Everybody agree? So I'm going to look for a second calculation triangle that involves 2 measurements that I know and then side AC. I think the obvious one would be the triangle ACD. Everybody see that? So to solve for AC, I can just do the Pythagorean theorem. I get the square root of 1348. I think that's 36 and change. So now that I know that, I can plug that in onto the pink triangle. I wrote this as a decimal rather than a square root because when I was making the pictures, it was getting to be a really big hassle to try to get the radical to go in there. So I just said, forget it, I'll just make it a decimal. But again, just Pythagorean theorem again. Oops. And here I used the radical because it made the arithmetic a little bit easier, because when you square the radical, it's 1348, you know. Anyway, so that comes out to be about 38.33 centimeters. Taylor, you're making a head tilt like my dog does when it's confused when I'm trying to get it to do something.
Did you just compare it to a dog?
No, I'm saying that you used...
I know, I'm sorry.
That it reminded me of what, like, my confusion.
No, it was
It's
accurate.
like,
It was accurate.
that was, but it was kind of confused head tilt.
Yeah.
Yeah.
I'm having to put.
Maybe I'm comparing my dog to you.
I don't know.
Is that a
if
better
it's any
version?
Okay. Okay. So, how do you know what AC is?
That's what we solved in the previous step.
Okay. I missed that slide because I was writing.
That's
But-
okay.
All right. Hold on. Now I need to get
So I did the Pythagorean theorem on a different triangle that had the side AC in it.
there. Oh, you like.
Yep, I just took the bottom. Cool?
Yeah. All right. Never mind then.
No problem. Okay. Another example, this one's a little bit more involved. So it says EABCD is a square-based right pyramid with sides of 12 centimeters. You can assume when it says sides of 12 centimeters, it's talking about the sides of the square base. The height of the pyramid is 9.5 centimeters. We want to calculate the length of EC. Let's do that part first. So I'm going to start by drawing my square pyramid and identifying a calculation triangle that involves EC. So that's what I've highlighted here in pink. Once again, EF, I know that's the height of the pyramid. It was given to me. But FC, I don't know. And EC is what I'm looking for. In order to find EC, I'm going to have to figure out what FC is first, right? Okay, I think there's two obvious calculation triangles you could use here. Does anybody see one? To find FC. I would do one, I think, is CFD. That's a right triangle. Now, why is that a right triangle? Doesn't look like one. So I know in a rectangle, the diagonals are perpendicular to each other. That's an old geometry theorem. So I know that this angle F is going to be a right angle. And in a parallelogram, the diagonals bisect each other. So I know FC and FD are going to be the same length. So I can just say x squared plus x squared equals 12 squared and solve for x. Now I had to pull two old geometry theorems to justify that to you guys. Do you think I'm going to expect you to also recall these old geometry theorems? You don't have to cite those to use them. And the nice part about those quadrilateral theorems is it looks like what it is, right? If you draw the diagonals of a square, they look perpendicular and they look bisected. They are. You don't have to cite a theorem to use that. I will whenever I do it because it's good review and that's the standard I set for myself, but not the expectation for you guys. Everybody still okay? However, that's not the calculation triangle I think is the easiest one to use. Instead, the one I would use would be CAD. And that'll allow me to solve for AC using the Pythagorean theorem. And again, since I know that the diagonals of my parallelogram bisect each other, I know that FC is just half of AC. So once I have AC, I know that FC is just half of that. And now that I have AC, I can go back to the pink triangle and solve for EC. Everybody feel good with that? Yeah, Serge?
So I see like you have like the CD, that's 12 centimeters.
Mhm.
But how did you get like the other angle measures? Like, how did you get-
Square base. So every side is 12.
Oh.
Cool?
Yeah.
No problem. Sometimes the reading is got the important piece in there, right? No problem. All right. So then to solve the pink triangle, we got the value for FC from before. That gets me my Pythagorean theorem. EC. Notice that all the things I'm doing is just like right triangle stuff, right? Lots of Pythagorean theorems, no big deal. Now I might have to use 2 triangles to get all the stuff that I need, but like, from a calculation standpoint, this is pretty easy, right? The complicated part is like picking out the stuff that you need to get the stuff that you want, right? Finding the right triangles that you need in order to get all the pieces you need in the where you need it. All right. There are 2 more parts to this question. The next part says at point M, marked halfway along one side of the base, calculate the length of EM. So here's M. I put it in between there. And I drew a calculation triangle here in blue. So EF, I know, is the height. That's still 9.5. And I said FM is 6. How did I know that?
It's half the length of the side.
Yeah, so again, if AD is 12, like this length would be 12. And I know since this is a square, F is like the centroid, the point exactly in the middle of it. So it's bisects that 12. Everybody's okay with that? So I can then Pythagorean theorem. I get 11.24. Cool with that? The last part then says, why are those not the same length? Well, I think the best answer is if I look at the triangle EMC. You see that triangle there? That's a right triangle that includes both of the segments. M is the right angle, which makes EC the hypotenuse, which sure as heck can't be the same length as a leg. Everybody agree with that? I think that's the best answer. Apparently when I wrote this some years ago, I didn't. My answer was, well, they're just like, one is a slant edge and the other is like the height of one of the faces, of the triangular faces. Like, okay, yeah, that's true also. I like my first answer that I gave you better because it's like definitively that they can't be the same. Like, this is still, okay, they're different parts of the thing, but doesn't really tell me why they can't be the same length. Why couldn't those 2 things be the same length? I mean, my answer was, the first answer is better. Current Kulik was smarter than, I don't know, 5 years ago Kulik or whoever wrote this thing. I think I wrote this, made this PowerPoint. Another example. Here we go, we got a cone here. We're told that the AB has length 11.3 and angle ABC, so angle ABC is 53. This little notation is another alternative way of writing an angle. I think it's more popular in Europe. So that's 53. So the calculation triangle that I was interested in, I drew here and shaded. So BDC is my calculation triangle. Now, obviously, I have BC. That's 11.3, right? What's going to be the second measurement that I need or that I can get out of this?
BC.
Right, BC is what I have in the shaded triangle. And I'm going to need two measurements in a right triangle in order to solve it. So what other measurement can I get inside the triangle BDC? What piece of given information haven't I used? Haven't used the angle, right? So what can I say, what can I do with that ABC is 53? What can I do with that? Well, I can't use the angle ABC and use SOHCAHTOA because it's not a right triangle.
Well, you can split in half, right? Because doesn't BD divide ABC evenly?
Why?
Because the cone, the slants are equal all the way around.
So if I look at the triangle ABC, what kind of triangle is that?
Isosceles.
That's why BD is going to be an angle bisector, in addition to it being an altitude, in addition to being a side bisector. So this is true only for isosceles or equilateral triangles. I believe in chapter 7 we had a test question, a story problem where like there's a flagpole in between two people. And everybody wanted to put it in the middle, and it's like it's not an isosceles triangle. That flagpole can't be in the middle. You guys kind of remember that? So part of the reason why we're going back and like hammering this again, because I know a lot of us made that mistake once already, so I want to like really hit it again. That unless you have an isosceles triangle, an altitude is not going to be an angle bisector or a side bisector. Okay? Now, the good part is if we're working with cones, I should say with right cones, what are we always going to have? An isosceles triangle. So this is what we have. We have two measurements now, an angle and a side. What do I need to use then to solve for that radius? SOHCAHTOA.
Yeah.
So what side am I looking for? Relative to the angle? Okay, what side do I have? Hypotenuse. So what do I want to use? Sine. There we go. Is that okay with everybody? Again, by and large, pretty easy calculation-wise. The hardest parts, just kind of setting everything up, right? Is getting the pieces that you need. But not so bad. This is where we're stopping.